Welcome back to ECE 441. Your passport is due today. That's your ticket to everywhere, or at least everywhere in this class. But that will allow me to, or you can remind me what your name and face, what pair of those go together so that I can try to remember that. Today what we want to do is pick up with where we left off on the mass spring damper system and continue showing these interrelationships between the different ways of representing those models. And in particular, today we'll start with trying to find a state space representation for the mass spring damper system. Then we will go into an all-integrator block diagram, and we want to start feeling comfortable with those different representations so that if you see a state space representation, you might visually start to see that as an all-integrator block diagram, and that might give you better intuitive insight into what is happening or what you see is going on in that particular system dynamic situation. Then we'll try to relate that to another way of thinking about a system, and that's by means of a Bode plot. What does the mass spring damper system look like in its Bode plot representation? And actually, to get the Bode plot, it's more convenient to start with the transfer function, g of s, and that's not, well, I guess we ended our last lecture with g of s, but there are many different ways of finding or determining the transfer function of a system based on what particular representation we have. We could have a state space representation, we might have a block diagram representation, we might have differential equations. All of those we want to be comfortable pushing those to a g of s or obtaining a transfer function representation. Let's then get started. And this mass spring damper system, you may be thinking I'm belaboring it quite a bit. If you think that, then, well, just grow some patience, because this is actually the system that you're going to be using in the lab. This is the system. It may not look this same way, but this is the schematic representation of what you will be playing with in the lab. In the lab, you'll have this little carriage, and you'll be able to put masses on it, and that's why we can have many different system combinations in the same class. You'll have some position that you can measure in that system. You will also attach a spring, and there are several different springs, and so we can have different combinations of springs. We have a glass cylinder that basically provides friction for us, and you can kind of visually see that. We're not going to adjust B, we're just going to leave B as it is. I don't want you to try to be adjusting certain thumb screw type devices to adjust the B. We'll just leave it as it is, actually without the plug in place. And now that particular configuration can give us 15 different systems to play with in this particular class without any real major problem. We have then the variables of interest, which were the position and the velocity. And based on that, we derived, oh, and I didn't apply an input. We will be applying some input. And let's generalize it a little bit. Let's just say that we have some scaling factor, and I'll call that capital gamma. So now we have a scaling factor. U is our adjustable signal waveform, U of t, and that gets weighted or scaled by a gamma, and that's the force that's being applied to this mass. If we do that, that changes the equation ever so slightly. We have the force external equaling mz double prime plus bz prime plus kz, and that's what we derived last time. It's just I've modified it slightly by introducing that scaling factor gamma. What we want to do now is find a state space representation for that particular set of equations, or that second order system of equations. And I'm putting the A in quotes because a state space representation is not unique. We could come up with many different state space representations. It depends on what you define as your state variables. But they are still going to be modeling the same system. Even though they may look different, they will actually be encompassing the same system. In this particular case, this was a second order differential equation. Because of the z double prime, or that because of that acceleration, or we have a second derivative in play. Because it's a second order differential equation, we actually will be finding or using two state variables to define a state space representation. And these state variables, what they do is actually included in the name. They basically contain information about the state of the system. So state variables possess the state, or you might think of the condition, of whatever dynamical system that you're interested in. In this case, it's this mass spring damper system, and I may just be calling it the MSD, the mass spring damper. And the reason why we concentrate on states or try to identify state variables is because if we now take the present and future inputs together with the present time state values, here you might be thinking this is now, whoops, u of t, where we have now this t. It could be a vector in general. Greater than or equal to t naught. We have our vector, our state vector, at the present time. So this is also potentially a vector, and t naught is the present time. And this and or plus sign is really sort of this with. So we combine the present state of our system together with the present input and all future inputs. That's this t greater than or equal to t naught. And that will allow us to determine what the system is going to do in terms of its state behavior for all future time. That's the power of this state space representation. So this now allows us to find or to compute x of t for t greater than or equal to t naught. This state space representation is then a powerful tool to possess. Now, to do that from this second order differential equation that we're starting with, what I like to do is simply isolate on the highest powered derivative, especially if you just have a nth order differential equation. You simply solve for that nth derivative term, and start writing or determining your state space representation based on that. Let's now solve that second order differential equation for the highest power derivative. Meaning I now have z double prime by itself isolated on the left-hand side of the expression, let's say, and now I've had to divide everything by m, and pushing everything else on the opposite side of the z double prime, I end up with a minus b over m z prime minus a k over m z plus this gamma over m times u. That's now the same dynamics, it's just been rewritten. What we want to do now is actually find a collection of first order derivatives. We want to find state variables and their dynamic behavior. So if we have 4 state variables, an x sub 1, an x sub 2, an x sub 3, and x sub 4, we want to find an x1 prime equation, an x2 prime, an x3 prime, and what's their time rate of change, and we want to describe that time rate of change in terms of all of the other state variables and the inputs. We can't have any derivatives of states in the description of those state space representations, in the state variables, I should say. So now what we're wanting to do is we are looking for, from this particular representation, we are looking to obtain 2 first order differential equations, and those 2 first order differential equations in general will be coupled, meaning you're going to have x1s and x2s on the right hand side of those x1 prime and x2 prime relationships. Here's where the variability could come into play in the state space representation is by however we define the state variables. Let me just define in this illustration the first state variable, which I'm saying is a variable x with the subscript 1. That's going to be my position. And the next state, I said I needed 2 states since it was a second order differential equation. Let me allow that to be the velocity in this particular case. And now I can actually find an x1 prime equation and an x2 prime equation. That's my idea, or that's what I want to be able to do. And that's what I need. I need an x1 prime equation and an x sub 2 prime equation, and those need to be in terms of, as I just said, the state variables themselves, x1 and x sub 2, and any inputs that I might have. These are the states. It's not the derivatives of the states that I can use. I just need to have x1, x2 without any primes on the right-hand side. If that's what I'm looking for, now I need to find an x1 prime equation. But by definition of how I defined x sub 1, if I take its derivative, that's just z prime. And now what I really want to do is write that right-hand side in terms of state variables. And in the way that I've defined these state variables, it's either obvious or it's kind of hiding in front of your face. But if you look at what we want this on the right-hand side to be written in terms of x1, x2, and u, or combinations. Well, now if I just see z prime, oh, that's actually one of the states that I defined, so indeed I now have that state space equation determined, this is now simply x sub 2 by definition of how I defined x sub 2. So now I have one of my first order differential equations. That's going to be x1 prime is equal to x2. Now I need to find an x2 prime equation. x2 prime was, if I look at the definition, that's the derivative of the velocity, meaning x2 prime is just the acceleration. But I've already solved for the acceleration right here. And now what I want to do is try to replace all of these z's and z primes with state variables. And in this case, it's right there. This z I will replace with x sub 1. This z prime I will replace with x sub 2. And now I have my second first order differential equation. And it's coupled to the other one. Meaning now my x2 prime, which is z prime, is actually minus b over m x sub 2, that's the velocity, minus k over m x1, that's the position, plus gamma over m u. And that's now my second first order differential equation that I was trying to create. And now what I want to do is actually put those into the standard form. The standard form is going to be the vector of x's differentiated once equals some A matrix times the vector x plus an input matrix B times the input u. And then I want to be able to identify output variables, y, that could be linear combinations of the state and input. This is now the generic state space representation. Meaning if I started with 5 coupled first order differential equations, I will be trying to put them into this standard form. An x prime equal ax plus bu, y is equal to cx plus du. In my case, the vector x is actually made up of two pieces, an x1 component and an x sub 2 component. So my x vector is only 2 tall, TWO tall, not TOO tall. It's Friday morning. Nothing's funny, is it? But now we want to build this up. We have an x1 prime and an x2 prime, but that's now a vector x. So that's my x prime vector right there. I'm just stacking up all my derivatives. And now I need that to be some matrix A times the vector x. And I need to add in some matrix times the vector u. And in this case, the vector u maybe doesn't look like a vector to you, but you can call it a vector. It's a 1 by 1 vector. It's a scalar, but it is a vector. It's 1 row tall and 1 row wide. X is a 2 by 1 vector. It's 2 tall, 2 variables tall, and 1 wide. Now, in order for this state space representation to make sense, the A matrix and the B matrix have to be compatible with this expression. And by matrix multiplication, we already know the width of the A matrix, or how many columns it has, because we have to have as many columns as we have rows in this state vector x1 and x2 if A is going to pre-multiply x. So A has to be, in this case, a 2-column matrix, and it has to be as tall as what's on the left-hand side, or what it's equal to. It has to be 2 rows tall. A is always square, actually. And in this case, it's the same squared dimension as the number of state variables that you have. If we had 5 state variables, A would be a 5 by 5 matrix. In this case, we have 2 state variables. A, our A matrix, is a 2 by 2 matrix. And if we have a 2 by 2 matrix, then we have 4 elements in that matrix. And what we now want to do is identify each of those 4 element values. And we go up to the x1 prime equation, and we say, okay, the very first row, the top row in that matrix representation in the state space needs to give me x sub 2 on the right-hand side. So now I come over here and I go 0, 1 will pull off what I need. And how big is my input matrix B? How tall is B? It has to be compatible with the left side, doesn't it? And my U determines how wide it is. And U was only one scalar. It was a 1 by 1 vector. So my input matrix B is this column matrix that's 2 by 1. And what part of U, or how much U, comes in to form x1 prime? Nothing. So we already know the top row of the input matrix B. And that's now half of the state space representation's construction. Now we get into the more interesting part in forming x2 prime. It has a little bit more structure to it. But right now we've just written basically x1 prime is equal to x sub 2. And that basically says the position's derivative is the velocity. Duh. But that's what we need to keep track of that. MATLAB needs that. Now what we want to do is say, okay, how's the acceleration defined? And that's now a function of the position, velocity, and the force, the input. And that's what's going to come in the bottom piece. We go back a little bit and we say, okay, x2 prime, I need to build that up. And maybe I wrote this in the wrong order in terms of filling in the matrix variables, but what do I want in the 2, 1, the 2, 1 position of the A matrix? Minus k over m. Does everybody see that? I need the variable that's going to be pulling off x sub 1, and in this case it's minus k over m. That now pulls off the minus k over m x1 piece that I need. What's in the 2, 2 element? That's the minus b over m. And my input matrix now has something, because that second differential equation does contain an input piece, and that's now gamma over m. Where we've just concluded then that this A matrix is a real matrix that's 2 by 2, and we will call that, or I will call that, possibly sometimes the system matrix. This is a system, x dot equal ax plus bu, y is equal to cx plus du. That's the system, but the system matrix, which basically keeps track of all the internal dynamics of our system, is all possessed right there in that system matrix. Our B matrix, in this particular example, is a column vector that's 2 by 1, and that's what I am calling my input matrix. And if I now say, well, what's the output y? I really didn't say what I was interested in terms of my output variable, so let's just pick one. Let's just say that the output, for illustration purposes, let's just let that output y be the position. Actually, I just solved the problem. The position, z. So now we have y. Somebody says, I want you to measure the position. Or that they could say, I want you to measure the position and the velocity, or I want you to measure the position plus 2 times the velocity, or I want you to measure just the velocity. Over in the lab, effectively, in the second lab, we'll assume that we're measuring the position and the velocity, that we'll have both of those states available to us to use. In the third lab, we'll say, nope, we don't have the velocity, all we have is position. Good luck with trying to control this system. Okay, that's what we're going to start learning or doing. Now, if this is the output, if the output is the position, now we can build this second half, the output equation, up from what we now know. We now know that y is going to equal something times our state vector plus something times the input vector u. And that something has to be, those matrices have to be compatible so that this equation makes sense. And how many outputs did I pick in this particular illustration? I just picked one, didn't I? So I only should have, this y is a vector in general. It's a 1 by 1 vector. It's a scalar. So whatever we have on the right-hand side, it better give me a scalar after all the multiplication is done. I have a 2 by 1 vector. I need to multiply that by the C matrix. The C matrix will be dimensionally 1 by 2. And how big is the D matrix that's multiplying U, the vector U, and producing the vector Y? It's 1 by 1. Now, what are in those three positions? What's in the 1, 1 position of my C vector, or C matrix? And then I don't have any direct input into my output Y, as I define my output. In some systems, you might. Here, then, what we have, this is our C matrix, which in this case is 1 by 2, and I will call that the output matrix. This is the D matrix, and it's a whopping 1 by 1, and I will call that the direct feed-through matrix. And that's now my state space representation for this mass spring damper system. We have an A matrix, we have a system matrix, we have an input matrix B, we have an output matrix C, and we have a direct feed-through matrix D. And now, if somebody gives you a linear system that's 20th order, you can create its state space representation. If it was 20th order and it had 3 inputs and 2 outputs, now you know the dimensions of all of those matrices. If I could remember what I just said, I'd ask you the dimensions. What did I say? So if we had a system, here's a quiz. If we had a system that had, what did I say, 20 states? 20 states. It had 3 inputs, is that what I said? And 2 outputs. Now, what are the dimensions on A, B, C, and D? Does that question make sense? Is it clear what I'm asking? So the system matrix better be square, right? You better have the same rows as you have columns. And the system matrix is giving us all of the information about the dynamic internal dynamics of the system, and that's influenced by the states. This guy better be, the A matrix is 20 by 20. What's the input matrix? It has to be compatible with the left-hand side, so we know it has to be 20 rows tall, and now its width has to be compatible with the input vector, and the input vector we said was 3 tall. So this one now is 20 by 3. What about the output matrix? It has to be giving us the y, the output vector, and the output vector we said was 2. So this is now 2 by I have to go to Home Depot. I need a 2. Oh, sorry. It's not a 2 by 4, is it? Or a 2 by 6, or a 2 by 8. It's 2 by 20, isn't it? It's the dimension of our state variable. It's 2 by 20. What's D? What's the direct feed-through matrix? How many rows do we know it has to possess? It has to be the same number of rows as C and Y. That's 2. And how wide is D? It has to be the same width as the input is tall to be matrix compatible. So it's 2 by 3. And now you know, before you even start trying to write all these equations and find the system matrices, if I say the system matrices, that's A, B, C, D. If I say the system matrix, that's A. Is that making sense? If I say the input matrix, that's B. But now you know the dimensions of all of these matrices before you start plugging them into MATLAB or something else. All right, now, based on this state space representation, I would like to sketch an all-integrator block diagram that might give us a better visual perspective of what's going on, the interactions that are taking place, which you'll start to see when you look at these representations enough. But right now, let's say that that's not that clear to us, although this one's not that complicated. But let's look at an all-integrator block diagram for this particular system. And by that I mean I want to have integrators and summing junctions and gain blocks. That's all I want in this diagram. In this particular system, how many integrators do I need? I need 2 because I have an x1 prime I need to get x1 out of, and I have an x2 prime I need to get an x2 out of. So I just need the number of integrators that I need is equal to the number of state variables. So if we're looking for partial credit, you'll get half a point out of 50 on that question if you just sketch this. If I say draw the all-integrator block diagram, boom, you give me 2 integrators. Okay, at least they know that there should be 2 integrators in this block diagram. Seriously? No, I said 0.5 out of 50. Yeah, that's not 50%, is it? I wouldn't give you 50% by showing me 2 integrators. You're lucky that I gave you a 1%. I'm kidding? No, I don't kid around. All right, now what do? Now we need to put some summing junctions in here. And maybe the easiest way to sketch these all-integrator block diagrams is to say, okay, if I have these state variables and I have their derivatives and I actually want the state values, why don't I just inject those derivatives as the inputs to these integrators? That seems pretty logical. So let me just say that I will push in through here. Let me call this x1 prime, and let me call this the derivative of x sub 2. And now what I want to do is I want to make the inputs, so those are the outputs of my summing junctions, are x1 prime and x2 prime, my derivatives, and those derivatives are going into the outputs, I'm sorry, these derivatives are going into the integrator, which when they come out the other side will give me x1 and x2. And x2 may not be connected to that summing junction, but in this case it actually is. What creates x1 prime? What needs to sum together to give me x1 prime in this particular example? Just x2. So I don't have to feed anything more into the inputs of that summing junction on the rightmost summing junction. What do I need to combine or sum up to create x sub 2 prime? If I go up here to my state space representation, x2 prime, let me start at the right. That's a piece of u, isn't it? The input u, not y-o-u. All right. So this is now gamma over m and u. That's part of x2 prime. Is everybody okay with that? We're trying to make everything that needs to come in to the summing junction that's necessary to create x2 prime. We also need to pull off some velocity piece. So working now from the right to the left, I need to scale the velocity by minus b over m. So here's the velocity. I'm going to scale it by minus b over m, and that's going to go into that summing junction also. And finally, I have a piece of x sub 1, which is minus k over m. And now I have my three pieces that combine to form my x sub 2 prime. Now what I need to do is create my output. And my output could be a linear combination of the states and a piece of the input. So I generically could have something coming from x2 with a gain. I could have something from u and a gain, and that's my d piece, isn't it? And I could have, whoops, let me just be a little bit more general. I could have some gained version I don't know why I'm wanting to do highlighter, but I'm trying to show you that it's not happening in this particular case, and this was one way to do that. In this particular example, all I have is my output y is made up solely of x sub 1. If I go back to my output equation, it was only y is equal to x sub 1. And that's what I've created here. And I had no x sub 2, and I had no direct feed through. But in general, I could have those. And that's now my all-integrator block diagram for this mass spring damper system, which I'm having trouble. Well, if I would have just said, okay, enough is enough. Let me just call that the output, which it is. Then I could show it all on one screen. And this is a time domain representation. That's the all-integrator block diagram in the time domain. You could very easily put this into the frequency domain because you may be finding frequency domain block diagrams occasionally. So if we wanted to put this into the frequency domain, what would we need to do? Now we have to worry about these integrator blocks. That's a time domain operation, isn't it? We're integrating in the time domain. But as an operator, if we integrate in the time domain, what does that look like as an operation in the frequency domain when we're using Laplace? If I said, okay, here's a variable and I want you to integrate it in the frequency domain, what would you be doing? 1 over s, wouldn't you? You would say, oh, I need this 1 over s operation, and that will be equivalent in the time domain of integrating. So now the only thing we have to do to put this into the frequency domain is replace those integrators with 1 over s's, and we're in as blocks, as operations, and now we have a frequency domain block diagram representation. The gains don't change, the summing junctions don't change, the pattern, the interconnection structure does not change. If we wanted this in the frequency domain, this block diagram, now we can sketch it. We could say, well, that's trivial after what work I've just done. I now have these 1 over s blocks. I'm not even going to worry about a summing junction between those two because it feeds directly in. I have a summing junction here. Here's gamma over m. Here's where you would lose 49.5 points out of 50, is if you put this as u of t. It's not u of t, it's u of s. Textbooks do it all the time, but you can't do it in this class. This is u of s because we're in the frequency domain. So that's the transform of the input. Coming out here is the transform of the output, which is y of s. And now we need to feed all of these back. Here's minus b over m. And minus k over m. And that's now our block diagram in the frequency domain. And now, if you could do block diagram algebra, you have the transfer function of your system, because the transfer function is the transform that relates the input u of s to the output y of s. And if we could do some block diagram algebra, we would be done. And how could we do that to find a g of s? If we wanted to sketch the Bode plot now of this system, let's say we need g of s. Well, we could get g of s, as I just indicated, from, let's say, 1, the block diagram. And really, you could get it from either one, but more directly, you could get it from the second one, the frequency domain version. We could also get the g of s directly from, with some algebra, the state space representation. We could also get g of s, which we did last time, from the differential equation. Now, do you want me to start all of those representations, or do you just want me to sketch the Bode plot just so you know what it looks like before you sleep on it all weekend? You want to start feeling warm and fuzzy about all these representations. Let me just sort of give you what G of S is, and we'll prove that on Monday, or verify that on Monday, and then we'll sketch the Bode plot today before we go home, because I know you're really excited about seeing that Bode plot. I don't want to keep you in suspense all weekend. So let's just pick some numbers for M, gamma, B, and K and produce a G of S. So if I do that, I hope I've done that somewhere. Let's just say, for purposes of reducing the suspense, let's say that, what did I say? Let's say that the mass is 2 kilograms. And what is 2 kilograms? So about a half a gallon of milk. So if you want to know what is 2 kilograms, now if you go into the store this weekend and pick up you'll go to the dairy section and pick up, please, go and pick up a half a gallon of milk, and you go, oh yeah, that's the mass that we were talking about in class Friday. I always say a gallon of milk is 8 pounds, roughly. A gallon of water is about 8, and I'm not distinguishing between water and milk. So I'm saying, and you just said that 2 kilograms was about 4 pounds, so half a gallon. Okay, it's round numbers. We're trying to get a gut feel for this. You're holding me to these 0.5s, aren't you? All right, so now M is equal to 2, K is 700. What else do I need? How about B? The damping, let's not have much damping. That's 5. And let's say gamma is 700. If we play through the numbers, and you can do that tonight, I know you'll want to do that before you go to sleep. This is now 350 over S squared plus 2.5S plus 350. If I'm sketching the Bode plot, what do I need? You need a graph. I need some paper, but you can just do this on an envelope. You need to know the poles and zeros and the gain, right? What's my DC gain of this transfer function as I've created it? The DC gain is 350. Anybody, we all agree? Look at it again. So the DC gain is G of what? When S is at 0, right? DC. So G of 0. So I tricked you, right? If we cover up these, then it's 350 over 350. The DC gain is actually 1, isn't it? So in a Bode plot sense, it's 0 dB. So we're starting at 0 dB, and then what do? Do we have any zeros? We don't have any finite zeros. Do we have any poles? Yes. How many poles do we have? 2. So now we know we're going flat, and then we're going to break, maybe twice. But if you look at this, this is actually complex poles. And these poles are at minus 1.25 plus and minus J 18.67. And we said we had a DC gain equal to 1 because that was G of 0. So we need actually, to be really quick, we need the natural frequency of that, and that's going to tell us sort of the location where we break. And roughly that 1 gets dominated, so this is about 1.7. We have a very small damping ratio. Where are these poles in the S-plane? Wow, I'm just starting, getting excited. They're up here, aren't they? They're very close to the imaginary axis, and they have a large imaginary piece. a large omega sub d. So these are not going to be damped very much. There's going to be some ringing. If we had them further into the left half plane, we would have a picture that did something like this. And this point here would be this 18.7. This slope is 2 minus 20 dBs per decade. But because of the low damping, this is going to be 0 dB, and then it's going to do this. So that's what our magnitude is going to look like for this mechanical system in dB. This is 0. And we'll have to figure out the other pieces when we return on Monday. But that'll at least, I think, get you calmed down a little bit. I know you'd be excited all weekend if I didn't show you a little of that. So we'll pick up at that point or somewhere on Monday.